An AI model does not learn because it understands data. It learns because we give it a numerical objective and repeatedly adjust its parameters to make that number smaller or larger. Everything else, intelligence, pattern recognition, language ability, emerges from this simple loop. If you truly understand loss functions and optimization objectives, you understand the core engine of modern machine learning. At the most fundamental level, a loss function is a mathematical rule that measures how wrong a model's prediction is. The optimization objective is the broader goal that tells the training process what direction to push the model's parameters. In many cases, the loss function and the optimization objective are the same thing, but conceptually it is useful to distinguish them. The loss function evaluates individual predictions or batches, while the optimization objective defines what the training procedure ultimately tries to minimize or maximize over the dataset. Imagine a supervised learning scenario. You feed an input into a neural network and it produces an output. You compare that output to the ground truth label. The loss function converts the difference into a single scalar value. That scalar becomes the signal that drives learning. Without the loss, the model has no notion of error, and without error, there is no gradient, and without gradients, there is no learning. The choice of loss function is not merely a technical detail. It encodes what you care about. It defines the geometry of the optimization landscape. It determines how sensitive the model is to outliers, how gradients behave, and sometimes even what kind of solutions are reachable. Two models with identical architectures but different loss functions can behave dramatically differently. Let's start with regression problems because they provide the cleanest intuition. Suppose your model predicts a continuous value, such as house prices. One of the most common loss functions is mean-squared error. Conceptually, you subtract the predicted value from the true value, square the difference, and average across the dataset. Squaring has two important effects. First, it ensures the loss is always non-negative. Second, it penalizes large errors much more heavily than small ones. This heavy penalty on large deviations makes mean-squared error sensitive to outliers. If your dataset contains occasional extreme values or noise, the model may devote disproportionate effort to fitting those points. In some domains this is desirable, but in others it is harmful. That is why alternative losses like mean absolute error exist. Mean absolute error grows linearly rather than quadratically, which makes it more robust to outliers but less smooth for optimization. Smoothness matters because most modern optimization relies on gradients. Gradient-based methods require the loss to be differentiable, ideally with well-behaved curvature. Mean-squared error is smooth everywhere, which makes gradient descent stable. Mean absolute error has a kink at zero error, which can make optimization slightly more difficult, though in practice it is still widely used. Now shift to classification problems, where the output is a probability distribution over classes. Here the dominant loss function is cross-entropy loss, sometimes called log loss. Instead of measuring numerical distance, cross-entropy measures the dissimilarity between the predicted probability distribution and the true distribution. The key insight behind cross-entropy is that it strongly penalizes confident wrong predictions. If the model assigns very high probability to the wrong class, the loss becomes extremely large. If the model is uncertain, the penalty is smaller. This property encourages well-calibrated probabilistic outputs and tends to produce faster learning and classification tasks. From an information theoretic perspective, cross-entropy connects directly to maximum likelihood estimation. Minimizing cross-entropy is equivalent to maximizing the likelihood of the observed labels under the model's predicted distribution. This is one reason it appears so universally in deep learning. It has strong statistical foundations. It is important to understand that the loss function shapes the gradient field. When you compute gradients through backpropagation, the magnitude and direction of updates depend heavily on the loss formulation. Poorly chosen losses can lead to vanishing gradients, exploding gradients, or flat regions in the optimization landscape where learning stalls. The optimization objective typically aggregates loss across the dataset. In empirical risk minimization, we minimize the average loss over training samples. However, real-world systems often include additional terms. Regularization is one of the most important. Regularization adds extra penalties to the objective to discourage undesirable parameter configurations. For example, L2 regularization penalizes large weights by adding the squared magnitude of parameters to the loss. This encourages the model to find simpler solutions and reduces overfitting. L1 regularization instead penalizes the absolute value of weights and tends to produce sparse models. These regularization terms are not measuring prediction error directly. They encode prior beliefs about what kinds of models generalize better. In modern deep learning, explicit regularization is sometimes supplemented or even replaced by implicit regularization arising from optimization dynamics, architecture choice, and data augmentation. Another major concept is the difference between training loss and evaluation metrics. Engineers sometimes assume that minimizing the loss automatically optimizes the metric they care about. This is not always true. Many real-world metrics, such as accuracy, F1 score, BLEU score, or ranking metrics, are non-differentiable. Because gradient-based optimization requires differentiability, we often train using surrogate losses that approximate the desired metric. This mismatch can create subtle failure modes. A model may achieve low cross-entropy loss but still perform poorly on the business metric. Advanced practitioners often design custom loss functions or multi-objective training schemes to better align optimization with real-world goals. Let's now discuss the optimization process itself. Once the loss is defined, training typically proceeds via gradient descent or one of its variants. The core idea is simple: compute the gradient of the loss with respect to model parameters and update parameters in the direction that reduces the loss. In practice, full batch gradient descent is rarely used because datasets are too large. Instead, we use stochastic gradient descent or mini-batch gradient descent. By computing gradients on small batches of data, we obtain noisy but computationally efficient updates. Interestingly, this noise is often beneficial because it helps the optimizer escape shallow local minima and explore flatter regions of a loss landscape. Modern optimizers like Atom, Rumsprop, and momentum-based SGD modify the basic gradient descent rule to improve convergence speed and stability. They adapt learning rates, accumulate gradient statistics, or smooth updates over time. However, despite their sophistication, they are all still fundamentally trying to minimize the chosen objective. Learning rate is one of the most sensitive hyperparameters in optimization. If it is too large, training becomes unstable and the loss may diverge. If it is too small, convergence becomes painfully slow and the model may get stuck in poor minima. Learning rate schedules, such as warm-up, cosine decay, or step decay, are often critical for successful large-scale training. Another subtle but crucial concept is the geometry of the loss landscape. Neural networks define extremely high-dimensional, non-convex optimization problems. Early intuition suggested that local minima would be the main difficulty. However, modern research shows that saddle points and flat regions are often more problematic than bad local minima. Flat minima, regions where many parameter configurations yield similar loss, are generally associated with better generalization. Sharp minima, where loss increases rapidly around the solution, often correlate with overfitting. Optimization dynamics, batch size, and learning rate all influence which type of minimum the model finds. In large language models and other generative systems, the optimization objective is usually token-level cross-entropy averaged over massive corpora. This deceptively simple objective drives remarkably complex emergent behavior. The model is never explicitly told grammar rules, world knowledge, or reasoning strategies. It is simply trained to predict the next token as accurately as possible. Yet, from this objective, sophisticated capabilities emerge. This highlights an important philosophical point: the loss function does not need to encode intelligence directly. It only needs to create pressure toward representations that capture useful structure in the data distribution. The richness of the data and the capacity of the model do much of the remaining work. However, objective design becomes more complex in advanced systems such as reinforcement learning. In reinforcement learning, the objective is typically to maximize expected cumulative reward rather than minimize prediction error. The loss function may involve policy gradients, value function errors, entropy bonuses, and other components. Credit assignment becomes more difficult because rewards may be delayed and sparse. Alignment training for large models introduces even more layers. Techniques such as reinforcement learning from human feedback involve training a reward model, optimizing a policy against that reward, and carefully balancing multiple loss terms to avoid reward hacking or mode collapse. In these systems, the optimization objective becomes a carefully engineered composite rather than a single clean loss. Multitask learning introduces another dimension. When a model must perform multiple tasks simultaneously, the total objective often becomes a weighted sum of several losses. Choosing the right weighting is non-trivial. If one loss dominates, the model may neglect other tasks. Adaptive weighting schemes and gradient balancing methods are active areas of research. There is also growing interest in curriculum learning and dynamic objectives. Instead of using a fixed loss throughout training, the training signal may evolve over time. Early stages may emphasize easier examples or auxiliary objectives, while later stages focus on harder tasks. This can significantly improve convergence and final performance. For highly technical practitioners, it is important to internalize that optimization is not just about minimizing a scalar. It is about navigating a complex high-dimensional energy surface under computational constraints. Numerical stability, gradient scaling, normalization layers, and mixed precision training all interact with the loss in subtle ways. One common pathology is gradient explosion or vanishing. If the loss landscape produces extremely large or extremely small gradients, training becomes unstable or stalls. Techniques such as gradient clipping, careful initialization, normalization layers, and residual connections are all partly motivated by the need to maintain healthy gradient flow. Another advanced consideration is loss scaling in mixed precision training. When using lower precision arithmetic, very small gradient values can underflow. Dynamic loss scaling multiplies the loss by a factor during backpropagation to preserve numerical signal, then rescales updates appropriately. This is a purely numerical trick, but without it, large models would train poorly on modern hardware. It is also worth discussing the distinction between optimization objective and true goal. In any real system, the loss is only a proxy for what we actually want. The gap between proxy and reality is where many failures occur. Models optimize exactly what we specify, not what we intend. Careful objective design, evaluation, and monitoring are therefore critical. As models continue to scale, objective simplicity has proven surprisingly powerful. Many of today's most capable systems are trained with relatively simple losses applied to enormous datasets. This suggests that data diversity and model capacity can sometimes compensate for objective simplicity. However, in specialized or safety-critical domains, more carefully engineered losses still provide major benefits. If you step back, the entire training pipeline can be viewed as a feedback control system. The model produces predictions. The loss measures error. Gradients propagate that error signal backward. The optimizer adjusts parameters. This loop repeats millions or billions of times. Stability, convergence speed, and final performance all depend on how well this loop is engineered. The most important intuition to leave with is that loss functions are not passive metrics. They actively sculpt the behavior of learning systems. Optimization objectives are the steering wheel of AI training. If you change them, even slightly, you often change the entire character of the resulting model. Whenever a model behaves unexpectedly, one of the first questions an experienced practitioner asks is, what exactly was the model optimized to do? Because in modern AI, the answer to that question usually explains far more than the architecture diagram ever will.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.